Hello everyone, my name is Mashuk Mohammed Mushraf and I welcome you to my class. So today's topic, I'm going to talk about half wave rectifier using diode. I'm going to consider ideal diode model to construct half wave rectifier. So first of all, the question arises that what is a half wave rectifier and why do we use half wave rectifier? So mainly what half wave rectifier does is it converts AC signal to DC signal. So it converts AC to DC. That's what half wave rectifier does. So if we think about it generally, in our house, when we are considering a current line or voltage line, um, we have AC signal, for example, something like this, right? This is actually an AC signal. We see that a current line or a voltage line may come out like this in our house. So this is our V input, and it changes with time, right? So there is a positive part of the signal and also a negative part of the signal. So we know that this part is what? This part is our positive. This part is when our voltage is positive, our current is positive, and this part is our negative. So when we have a source, something like this, so when it is in positive half cycle, we are considering this both of these full cycle. So this part is the positive half cycle, this part is the negative half cycle part. So when you consider positive half cycle, the polarity could be like this. The upper part is plus, the lower part is minus. So the upper part is in higher potential, the lower is in lower potential. And when we are considering the negative half cycle, then the current reverses, right? The voltage becomes opposite. So this is becomes my negative potential, and this becomes a uh, positive terminal. That is negative terminal. So this is what we get in our current line in our houses. So now, for example, now you want what you need is you want to charge your phone. You want to charge your phone, but your phone requires a DC signal to get charged. Okay, a phone requires a DC signal. So what is a DC signal? We know that a DC signal is something that does not change with time, and it always stays positive. For example, this is for let's say example this is 5 volt. So DC signal is constant, and also in one direction. So we want something like this to charge our phone. So we need to convert AC signal to something like this, which is a DC signal. So for this, we have some steps to do. First step is actually the number one step is actually to cut off the negative part of my DC signal. So negative part as in this part. So if I label it with red, so see this part is unnecessary and I don't need it because now I'm going to consider making my DC signal in one direction. The DC signal is basically one direction, but this is in both directions. Okay, so when I cut off this part, my signal that actually stays is something like this. If the positive part remains, the negative part is cut off, then the positive part remains. Right? So this is our positive part. These are positive, this is positive. So you see that there is no negative part. This is our first step, and half rectifier actually does that. The half rectifier's work is actually doing that. The second step could be, and in first step you can see this is still not fully DC because the DC is varying. So we call this part to be pulsating DC. Why pulsating DC? Because you see the DC is varying and as a like a pulse, right? It is going up and down. It is going up and down, and it is even though it is in one direction, but still it is varying. But so we still need to smooth it out, right? To make it in like almost constant. So in second part, what we do is apply we apply capacitor in half rectifier to smooth things out, and the circuit that actually stays behind is something like this. So it does not become completely zero. So it becomes something like this, and this happens with capacitor. Okay, and as you use more capacitors, because we know capacitor can store energy, charge. So so see, this becomes more smooth and it doesn't go completely zero. So more capacitor use, it becomes more smooth and it is actually almost touches the ground. So now we want to do the first step. First step is actually using the half rectifier to actually cut off the negative part of the signal. So let's see the circuit for half wave rectifier. What kind of circuit it is? So this is our input V in, and I've said that this is our AC signal, right? Then we have a diode. Then we have diode, and then we have a resistor. Okay. So these are V in, and we consider our output voltage to be over here. Okay. So let's consider this circuit one by one. Let's bring it over here. Let's draw it again. These are V in. So now I'm going to consider cycle by cycle. So first of all, I'm going to consider the first half cycle, which is this part, right? At this point, my V in is, I'm considering it to be positive. So what is my terminal? My terminal is the upper part is positive, the lower part is negative. So let's consider the positive half cycle. When it is in positive half cycle, what happens actually? So you can see when it is in positive half cycle, my voltage is actually higher over here, right? The potential is higher and lower over here. So as we know that, how does a diode work? A diode has a P junction and an N junction, and I'm considering it to be ideal diode, right? Ideal diode model. So we know that when the voltage in P junction is higher compared to voltage in N junction, in ideal case, the diode becomes short circuited. Over here, you can actually see the same scenario happening. You see the voltage at P junction is actually higher because this is plus, right? So actually over here, the potential over here is higher and the potential over here is lower. That means the diode will actually get short circuited, and you can get a clear path across, right? Because the current is also flowing in this direction. So the diode will let it pass through as well. And our output is over here. So you can see that the input that is actually coming, it completely goes through the output. I mean, it gets the voltage gets dropped across the resistor, right? The full voltage with no loss. And this also obviously I'm considering ideal model case. So at this moment, if I draw the output signal for this one, at this time, at this moment, my V in is completely V out, right? At this, if I extend this time, my V in is completely V out. That means the positive voltage remains positive voltage during the positive, I mean, when I'm considering the positive half cycle. So this is my V out. Now let's consider my negative half cycle. So what does it mean by negative half cycle? It means now I'm considering this part of the signal, this part of the signal. So let me draw it in another color. This part of the signal. I'm considering this part of the signal. Okay. So what happens in this part of the signal in V out, and this obviously with time. I'm drawing with time. So in negative half cycle, my terminals get what? Get becomes opposite, right? Because now the current is flowing in opposite direction. My voltage is in the negative half cycle, right? This is my negative voltage because it's less than zero. So that is in negative cycle. That means my terminal now becomes minus plus, not plus minus. At this stage, if you see this is minus and this is plus, my diode was over here, and you see um, here my P, this is my P junction, this is my N junction. At this moment, at this point, the voltage across the P is lower, right? Across P junction, because now this is negative and this part is positive. And in this case, it was actually my voltage across the P junction was higher in this case, in this scenario, right? But in this scenario, my potential across PP, which is actually a voltage in P junction, is lower than my voltage in N junction, because now the current is flowing in opposite direction, and also this is in my lower potential, this is higher potential. So what will happen at this moment? At this moment, as this is lower than this, we know in ideal case scenario, it becomes open circuit, right? It becomes open circuit because my potential voltage is across the P junction is lower than N junction. So no current can actually flow and complete the circuit, complete the whole circuit. For this case, you see, as this is open, my VR becomes zero, and this is for negative half cycle. That means for negative half cycle, when my V in is negative, the diode becomes open circuit, and this obviously in ideal diode case. And so no voltage actually passes through to V out. No current goes through V out. That means my voltage is actually zero. Then for positive half cycle, it will again become something like this. And then it will become zero again. This will continue. But if you see clearly, my AC signal got converted to what? Pulsating DC, right? And this is important. My AC signal got converted to pulsating DC, and this helps in and if I further use a capacitor parallelly, it will smooth out and it will actually become closer to a DC signal. This is what we are expecting. So for now, I've covered that how can we actually get from AC to pulsating DC. And if we connect a capacitor, we know capacitor can store charges. For that case, it will not become during the negative half cycle, it will not become fully zero. There will still be a voltage at some point, and then it will become clear, closer to a smoother DC signal, fixed DC signal, rather than pulsating DC. So thank you. This is it for this session. We will continue next session. Thank you.